Hello, ladies and gentlemen, and welcome back. Root Beer here, taking a look at question number 3 on our 2018 Hypatia contest. A sequence, T1, T2, T3, and so on, is defined by T1 is equal to 1, T2 is equal to 2, and each term after the second is equal to 1 more than the product of all the previous terms in the sequence. I think this is the definition of, what are they called? Euclidean numbers. Because don't you use this setup to prove that there are an infinite number of primes? Yeah, I think so. I think Euclidean numbers. I don't know if that's actually going to help us here, but maybe we'll start talking about prime numbers down here, and it will. So Tn plus 1, the next term, is 1 plus the product of all the other ones. Okay. For example, T3 is 1 plus T1 times T2, which is 1 plus 1 times 2, 1 plus 2, 3. Alright, so we've got 5 parts here. Sorry, not 5 parts, 4 parts here. I think I saw this 5 and my brain decided you're going to say that instead. But A part, what is the value of T5? And it looks like in all these parts we're getting to know T's, so we might want to look at all of them for a moment, but what have we got here? Prove that Tn plus 1 is Tn squared minus Tn plus 1. In C, we're proving that Tn plus 1 is a factor of their product minus 1. And then at the end, we want to show that T 2018 is not a perfect square. So we've got to start thinking of ways to show things aren't perfect squares, which I don't have many off the top of my head, but maybe B and C will give us a good way to do that. Okay, so for A, what's the value of T5? Well, pretty quickly we can just... It's a light bulb question, so you don't actually have to show your work. But there's not a whole lot to do, so 1 plus 1 times 2 times 3 is 1 plus 6. The next term is 7. And T5 is going to be 1 plus 1 times 2 times 3 times 7. And that'll be 6 times 7, 42. Plus 1 is 43. Okay. So that's T5. Now we might want to figure out T6 and T7 a little later. And interestingly enough, we don't have to work all that out again because B is going to tell us a faster way to figure out Tn plus 1. The question is, how can we prove that? Well, we probably want to start with one side or another. I'm going to start with Tn squared minus Tn plus 1. And what I'm going to do is I'm going to use the definition of Tn and the recursion that we know, and I should be able to rearrange it to get Tn plus 1. So this is equal to... What's the best way to say this? Tn minus 1, Tn minus 2, all the way down to Tn plus 1, squared, minus Tn minus 1, Tn minus 2, all the way down to Tn, or T1 plus 1, and then we add on another 1. Okay, so this one and this one will cancel out because this one is being subtracted. And then if we expand the square, we'll get Tn minus 1, Tn minus 2 times all the way down to T1 squared. It's a plus sign, so it's plus 2 times 1 times Tn minus 1, Tn minus 2, all the way down to Tn, plus another 1. And then we just need to subtract off Tn minus 1, Tn minus 2, all the way down to T1. Now, this part and one of these cancels, which is good. And then I'm left with Tn minus 1 times Tn minus 2. And I need to turn this into Tn plus 1. So, I've got the plus 1 here, so I want to keep this plus 1. I need to find a way to turn this squared plus another copy of it into Tn times Tn minus 1 times Tn minus 2 all the way down to T1. So I think it makes a lot of sense to factor this out. And what will be left with? So that got rid of one of them. And there'll be plus 1 for this part. And then we'll be left with another copy of Tn minus 1, Tn minus 2, all the way down to T1. But of course, this is exactly what Tn is. And that's all we need to do. We don't even need to explain what we're doing. As long as our steps are very clear, we go from one to another, and equal signs all the way through, that's fine, and that shows off b. So that's not bad, and it gives me a fast way to figure out my next term and my term after that, and so on, if I need them. Okay? And I might, as I try and explore D, because I feel like D, we might be looking at a pattern. I don't know yet. We've got C to do in between then, so what have we got? Prove that Tn plus Tn plus 1 is a factor of Tn times Tn plus 1 minus 1. Now, I like the product here just because we've got products in the original expression. I'm not the biggest fan of the plus sign there. And this needs to be shown for all integers n greater than or equal to 2, so this might be an induction, perhaps. Does it specifically only work? Like, why would it fail with 1 and 2? So 1 plus 2 is a factor of 1 times 2 minus 1. It's just too small. Okay, that makes sense. But should we be looking at this with an induction? Well, if we were going to induct, I would need to have, well, let's do this over on the other sheet of paper if I'm going to mess around with it. I would need a way to break down the Tn plus 1, Tn plus 2 minus 1 into something sort of involving Tn in the previous case or a previous case. Although usually we don't do strong induction on a high school level contest. And so, should Tn times Tn plus 1 minus 1 be a factor of this? It's a little tricky to work with. Now, one thought, maybe we can just prove it directly, like we did in B, although I'm not exactly optimistic that we can do that, but if I take Tn and Tn plus 1, it's plus 1, or is it minus 1? It's minus 1. Well, darn, I was going to say come along and multiply T1 through Tn minus 1 on both sides. Because then at least, then if I subtract another 1 and add on a 1, then this part here becomes Tn plus 2. And that would be, and then this part here becomes Tn, which is kind of nifty, but even if this is the choice of multiplying by this is kind of arbitrary. So, And then what does this sum here even look like? Well, we don't have to use this particular definition because thanks to B we know some stuff. So by B I know that Tn plus 1, all instances of Tn plus 1 can be replaced by this expression. Oh, and so Tn and Tn plus 1 will cancel out to be Tn plus Tn squared minus Tn plus 1. Those two will cancel and you'll get Tn squared plus 1. So that's, I mean, can we do something similar and just get everything in terms of Tn? Maybe. Tn plus 1 minus 1 is Tn squared minus Tn plus 1 minus 1, so that's Tn cubed minus Tn squared plus Tn minus 1. Oh, and this factors Tn squared plus 1. We get a Tn and then a minus 1. So yes, that appears to work. Now, why, if this is true, then why the n greater than or equal to 2 condition? Well, if n were equal to 1, then T1 is 1, you get 1 squared plus 1 times 0, so, but that's not 1 times 2 minus 1, which is equal to 1. So what's going on? What have I done wrong here? Oh. Silly me, this requires n greater than or equal to 2. Did I use that fact when I proved this? I suppose I used it by saying this, so since... I probably should mention that, actually. So, by recursive definition for Tn with n greater than or equal to 2, I completely skipped that pass. So that's why. It's because B doesn't work for n greater than or equal to 2. That's why. Okay. There, I was really worried there, because the math should work out. So... then Tn plus 1, we should probably say for n greater than or equal to 2 up here, which is equal to Tn squared plus 1, divides Tn squared plus 1 times Tn minus 1, which is equal to Tn plus 1 minus 1. There we go. That proves C. Okay. So we used B to prove C. Maybe we'll have to use C to prove D. So we want to prove that T 2018 is not a perfect square. And I'm willing to bet that 2018 isn't particularly special here. None of the other ones that we've looked at were perfect squares. So I'm actually inclined to believe that none of these are perfect squares. The 2018 is just a really big number, and we're probably going to have to maybe hunt for some patterns, I think. So let's go back. When we worked out T5, we worked out what T4 was 7, T5 is 43. Maybe work out the next one and the next one after that. None of these I should suspect are perfect squares, but maybe they have some other unifying property to them. Okay. So we know we've got 1, 2, 3, 7, 43. And these are indeed, these are all primes, but the next one, if I grab my calculator, and I can figure it out without having to multiply them all together, just do 43 squared minus 43 plus 1. Next one should be 1807, and I don't think that's a prime, but maybe they are all primes and we have to prove that. No, it's not a prime because this is 13 times something. Okay, that's what I thought. Good. Um, Alright, so I noticed other than the 2 here, they're all odd. Now, that's not saying much because you can have odd primes, but for n greater than or equal to 2 is odd. Since Tn will be 1 plus 1 times 2 times T 3 times all the way up to Tn minus 1. So this will be 1 plus 2 times something. Call it k. Actually, I prefer the little k. I wrote the big K because it was a big T, but I'm more comfortable with the little k here. So it's odd. Okay, so that narrows down our choices. If it were a perfect square, it'd have to be an odd perfect square. Now, none of these are perfect squares, and actually, they all have a remainder of 3 when we divide by 4, and that's something that's not allowed for perfect squares. So, this might be something that you know. It's a useful thing to know that perfect squares, when you divide by 4, either leave a remainder of 0 or 1. It is a fact you can just state, but I'll quickly prove it here. So for Tn to be a perfect square, for T2018, it must be, let's say, T2L plus 1. It must be an odd square. But that's 4L squared plus 4L plus 1. We'll just group it like this. If you've never seen this before, this is extremely handy. Just like when you divide a perfect square by 3, you'll either get a 0 or a 1. When you divide a perfect square by 5, I think you either get 0, 1, or 4. So these are useful things to know. Must leave remainder of 1 when divided by 4. Or you could say Tn needs to... Well, we need to show this. I mean... we need to show at least that Tn for n greater than or equal to 2 does in fact leave a remainder of 3, but this isn't too bad because for n greater than or equal to 2, Tn is 1 plus 2 times T3, T4, all the way up to Tn minus 1, but each of these is odd. So Tn minus 1 is a multiple of 2, not of 4. So Tn doesn't leave a remainder of 1 when divided by 4. It'll actually be 3. You'll leave a remainder of 3. Therefore, Tn for n greater than or equal to 2 is not a perfect square, so we were able to show the whole thing. And so 2018 isn't in specific. because that's the one they actually did ask about. But there we go. And it turns out Tn is never a perfect square, because the other two cases, 1 and 2, well, I guess 1's a perfect square. So the only time Tn is a perfect square is when n is equal to 1. So I like that. I can't help but wonder if there was a way to do D that involved C or B, because I didn't really use them. I mean, I used B to quickly find the 1807, but yeah, I suspect there's probably a way using C. But I can't think of it off the top of my head what it might be. Well, Tn plus 1 is a square plus 1, but that doesn't mean that... Also, it wouldn't necessarily... We're not talking about 2000... We don't talk about individual 2018s. I guess you could say T 2018 is 2017 squared minus T 2017 plus 1. But if that's a square... Yeah, you get a difference of squares here. But I don't see anything wrong with that. T 2017. I'm just gonna try and work this out. Is there a way to use C? Well, yeah, actually. Because the difference of squares would have to factor like this. And in order for it to be T 2017 minus 1, in order for it to be factored like this, both of these have to be less than T 2017 minus 1, but of course for any value of k this is going to be bigger, right? So I guess that would be a quick way to show that it doesn't work, I think. Interesting. Anyway, I think it's best we move on to question number 4. If you have another way to do D, I would certainly love to read about it in the comments below. But I think we're going to move on to our next question and wrap up our 2018 Hypatia. I'll see you in the next video.